Yo, where is my hat? God damn. Why are we stealing my hat? That's just diabolical, all right? You know what? I came here to teach you guys, and you guys are stealing my hat. Do you realize how cynical that is? I'm trying to cover my hair. Like, I'm trying to survive out in these parts. As a country boy, you know what I mean? Like, I'm a hunter and a gatherer. I gotta survive, and you guys are stealing my protection. I don't know how I feel about that. Anyways, back to class. All right, pay attention. We're talking about invertible linear maps. Can't be breaking character. I see what is that, a duck? That's a guinea. Wow. Wish I could show you guys the camera, but I legit spent like 20 minutes trying to set up this camera. It's like barely positioned on like the window of a car. Okay guys, shut up. All right, I'm trying to record a video. But it's like, oh my God, I swear if the wind blows the wrong way, it's gonna like topple over my phone. So let me just finish this video real quick before I lose our angle here. Hopefully I'm not decapitated this time. I wasn't too careful about that, but I'm just hoping that we are, because I elevated a little high, so theoretically, if you can see the extent of the board, you can see my head. But who wants to see my head anyway, am I right? Like, that's just, that goes without saying. The math is what matters, right? Okay, I'm gonna cut the yap and just get right into the math. That was way too much. So invertible maps, all right? Well, we know what maps are. We know what linear maps. Technically, I should be saying linear maps, because that's sort of the study of linear algebra. It's linear algebra. So usually when I'm talking about maps, you know, it goes without saying that they're linear, because of the field of study that we're considering in the first place. Invertible, if you've taken perhaps like a pre-calc class, you've probably heard of an invertible function, right? An invertible function, well, what is that? And why do we care? Well, invertible functions are nice in that, let's say you have a function f. I don't know, I feel like a lot of people have seen the following notation, f inverse, so the inverse of f. Now we know that such an inverse doesn't necessarily exist, and there's various examples of functions that don't have inverses. I mean, for example, I don't know why this is the first thing that I recall, but like sine of x, because, so you have your sine function, right? Oscillates like this. The thing about an inverse is that, notice how, if we consider it on its full domain, right, it passes over the same y value, like actually infinitely many times, but the point is more than once. And so what the inverse does is, if you think about it at a sort of like non-technical level, it swaps the x and the y values, right? And remember, what it means to be a function, we need to map a single point to another point. We can't map a single point to two different points, right? We can map two different points to the same point, but not the other way around. That's what we're doing here. We're mapping two different points to the same y value. But when we swap the x and the y values, suddenly we're trying to output two of the same x values to, we're trying to output one of x values to, like, actually in this case, infinitely many y values. If we try to write down an inverse, it would probably look something like this. Like, look, because if you think about it, right, when you do an inverse, you're trying to reflect over your y equals x, right? That's sort of how you visualize an inverse. So then it turns out to kind of like go like this. That ain't a function. Like, if you've taken any math class that you've discussed functions in, you know this isn't a function. Some people have seen it called like the horizontal line test to check for invertibility. And so that's just sort of like understanding, just a review of what an inverse is, right? So not everything's invertible, and that's an important thing. But sometimes we also take for granted, like, what if a function has two inverses? Is that possible? Like, if it exists in the first place, can there be two of them? Well, I want to show you guys that that's actually not true. First of all, just for some housekeeping, I want to kind of rigorously define what the inverse is, just in the context of linear algebra. I mean, it's going to be very intuitive if you already know what the inverse is. and you guys can kind of guess. So we're looking at some linear map T, let's say from, you know, two vector spaces, V to W. And we say, so this is a definition really. We say T is invertible if, well, if there exists some kind of inverse function, right? So if there exists like S from W to V, all right? Because remember, we're swapping sort of the domain and the codomain values when we're taking the inverse. So that other function is going to have to go in the opposite direction. So from that codomain to that domain, so that, well, if you compose them, right, if you take f of f inverse, in this case we're dealing with T, but just coming back to the f example, f of f inverse is the identity, and actually the opposite way around, all right? There are these things called left and right inverses. These are things that matter more in like group theory, but that's something that would be interesting to look into, and I might do some more stuff on group theory, perhaps, in the future. I definitely will. So that, what's true? Well, T composed with S equals S composed with T equals the identity. Again, remember f of f inverse of x, that is x, right? If such an f inverse exists. That's what you guys know about taking the inverse, and that's what's so nice. If you, basically, it just returns you back, like, if you consider the function where you compose f and f inverse, if you plug in something to that, it just gives you back the same thing. So it acts as the inverse, which is pretty nice. And so that's why we're exploring functions like this. This means the same thing. It looks like I'm multiplying T and S. TS is tough, and it also looks like I'm multiplying S and T here, but this is just concise notation for like T composed. So you also see T composed with S and S composed with T, but this is just brief notation, just to keep it easy. Keep track of all these things. Okay, that's the definition of an invertible map. So T is invertible if such a function exists. So now I'm going to prove the first like really simple result, which I just covered. Can we have multiple inverses? That's the question, right? So, so the question, right, is if, let's say T is invertible, can two inverses or more than one inverse exist? Okay. Okay, well, we never, like, if you've taken a pre-calc class, again, tying back all these kinds of concepts, you might remember, like, I don't remember there being two inverses for one function. Holy crap, hope you guys couldn't hear that. That freaked me out. Anyways, I don't want to be liable for any heart attacks. Gosh darn. Okay, anyways, you might remember, right, there cannot be two inverses, okay? But how do we prove that, like, in a rigorous way? Okay, well, this actually has a neat trick. So we're going to prove that inverses are, quote, unique, in that there's only one inverse for every function that is invertible. So suppose, and we're going to do it for sake of contradiction. So by way of contradiction, that's short for by way of contradiction, S1 and S2 are inverses of T. Well, what do we know then? We know that, well, what can we say about, like, I don't know, S1 of T? And there's various ways you can do this, okay? We want to show that S1 equals S2, okay? So we don't even need to consider it by way of contradiction. Sorry guys, I'm kind of doing this on the fly, genuinely. Living on the edge is fun. This is how I like doing things. So we don't need to do contradiction. If these are two inverses, that's not discounting the fact that they could be equal. Like, we want to show that S1 equals S2 because that would imply that there's no way you could get two different inverses without having to say all this jargon of like, oh, for sake of contradiction, S1 is not equal to S2. It works because then you can prove that S1 actually does equal S2. You get a contradiction, thus they must be equal, but it proves the same thing just in a more convoluted fashion. So we're going to assume these are two inverses. We want to show that S1 equals S2. All right, so start with S1 equals, how the hell do we get S2? Okay, well, we want to use this inverse property. And how do we bring S2 into the picture? Well, we know that S2 times T is identity. And we know that identity times S1 is just S1. So we know that S1 is identity times S1, or I shouldn't say times, composed with S1, right? The identity doesn't do anything. But the identity, like I just said, is, we could write it in various ways, right? We could say S2 times T times S2 of T, S1, right? Because S2 is an inverse of T. All right, well, we know that linear maps are associative. I didn't actually prove this. All maps are associative, but this is sort of like, it's kind of clear. I'll leave it as an exercise. If you want me to prove it, let me know in the comments for sure. So we can move around the parentheses. TS. Okay. All right. Well, what is this? This is also the identity, right? Because we assume that S1 is also invertible, or S1 is also the inverse of T. So this is just S2 of I, which is just S2. So what did we get? S1 equals S2. Boom. We proved that inverses are unique. All right, so without wasting y'all's time any further, because I've already yapped enough in this gosh darn video, in the next video, I'm going to continue on, and we're going to talk about, well, I'll figure out what the heck we're going to talk about. But anyhow, I'll see you then.